Alrighty, let's go ahead and finish up our long four-part lecture on limits. So today we're going to be talking about two types of limits, asymptote limits and infinite limits. And something that can get a little confusing is actually the names that some other people use to describe asymptote limits. Sometimes they call them limits at infinity or even infinite limits. So that can lead to some confusion on the distinction between these two types of limits. When I'm going through this, we're going to first talk only about asymptote limits, and then I'm going to do a little bridge to infinite limits. Just to be clear, asymptote limits will have the term infinity in the answers, so try not to let that confuse you between these two types of limits. I'll make sure to point out those differences though, so we never get confused. Let's go ahead and start off with an example of an asymptote limit. So we've got this limit as x approaches 1 of x squared minus 2x plus 1, all divided by x minus 1 cubed. And this actually looks like a limit that we saw previously. We saw this in the last lecture. And we might think right off the bat to try out a factoring and hope things cancel. Try that method, that algebraic method. But what we always got to do first is we always have to start with a direct substitution. I'm going to keep harping on that. We're going to take this limit. We're just going to try doing a direct substitution. We're going to see what happens. And if we do this, so I do my direct sub. I don't bother writing that limit as x approaches 1 anymore because I am evaluating the limit at 1 now. And if we go on and we do this, we will in fact end up with 0 over 0. I know a lot of the examples that we've seen end up with that. That's okay. We just know that we have an indeterminate form, and so we need to do some algebraic manipulation to this function, to this limit, in order to turn it into something that we can actually write down as our answer. So let's go ahead and let's do this factoring that we talked about. It may be tough to recognize right off the bat that factoring is what we need to do, but with some trial and error, you'd get there eventually. So let's go ahead and take that numerator, and if we factor this, it actually factors really, really nicely into a perfect square. So it'll factor into x minus 1 squared, and then let's still divide it by x minus 1 cubed. And now we've got some awesome cancellation here. So with this cancellation, we end up with the limit as x approaches 1 of 1 over x minus 1. And again, this is fantastic because when I look at this 1 over x minus 1, I know that there's no way that I can get 0 over 0 because the numerator is just 1. It's always just going to be 1. There's no way for that numerator to be 0, so I can't get that indeterminate form 0 over 0. So if we do our direct substitution here, I'm going to do this in a different color. If we do our direct substitution, we're going to end up with 1 over 1 minus 1, which is equal to 1 over 0. And if you see that, you might at first think, okay, indeterminate form, but this actually isn't an indeterminate form. It's not that 0 over 0. This is some number divided by 0. And hopefully what we can sort of think is any number divided by 0 is going to be really, really, really big, right? Because 0 is so small, it's like I'm dividing by something very, very small. So that's going to go into that numerator a lot. And so we would think that, sort of a naive guess here would be to say that this answer is equal to infinity. But here's the question, or here's the point that I would make. It could also be equal to negative infinity. We'll see this on a graph in a second. But really, when I'm looking at this, I don't really know whether it's infinity, whether it's negative infinity. Does this limit maybe not even exist? So I'd write DNE. We're kind of stuck here, and there's not a whole lot to do. So what I want to do here is I want to sort of go back up to this point and stop right here And let's do this limit graphically. So if we have 1 over x minus 1, we could do this graphically, and we could just look at a graph of the function 1 over x minus 1. And if I actually do that, I've got that graph shown right here. This is 1 over x minus 1. You can see that there's an asymptote at x equals 1, and that's expected right here. And if we're looking at this limit as x approaches 1, so remember graphically when we look at the limit, we're looking on both sides of that x approaching 1, and we're going to see what happens to the function as I approach it. And here's where I want to bring back the idea of left and right-sided limits. So if I look at x approaching 1 from the left-hand side, the function goes down and down and down and down, and it keeps going down forever as I get closer and closer to 1 from the left. So if I were to write out the left limit as x approaches 1 from the left of 1 over x minus 1, I'm going to get negative infinity because this goes down to, it just keeps on going down forever. So it's an extremely large negative number. We'll say negative infinity. Alternatively, if I approach 1 from the right-hand side, the function goes up to positive infinity. And that's fine and that's okay. We just have to realize that our left and right-sided limits are not the same thing. We have minus infinity for the left and we have positive infinity for the right. And because they're not the same thing, as we've seen before, if your left and right limits are not equal, if they don't go to the same value, then you end up with a limit that does not exist. So we would say that the limit as x approaches 1 of this does not exist. And that actually answers our question from back here on this slide of, where are we at? Are we infinity? Are we does not exist? Are we negative infinity? We're going to be at that DNE as our answer. And that's fine. That's an appropriate answer for this limit. And you can see that from this graph right here, that the left and right sided limits go to 2 different places. And so we get does not exist. So that's obviously the reason that this has happened. The reason that we've got does not exist is because of this asymptote. And that's why I like to call these asymptote limits, because there's generally an asymptote involved in them. Let's go ahead and do another example. It's going to look nearly identical. The only thing I've changed here is I've changed the exponent here from a 3 to a 4. And so with our work, we're going to end up with limit as x approaches 1. I'll copy this guy down, and I'm gonna go ahead and skip this factoring and canceling work because we pretty much just did it on the last slide. We're gonna get almost the same exact thing, except instead of an x minus 1 on the denominator, we're gonna have an x minus 1 squared. And so again, though, when I do my direct substitution, I'm gonna look at this, I'm gonna say, okay, direct sub, I'm still gonna get 1 over 0. And so I ask myself, okay, well, if I'm getting 1 over 0, is this infinity? Is it does not exist? Is it negative infinity? You might be tempted from that last example to just say, oh, well, we got 1 over 0 last time, and it was does not exist for the answer. So this is going to be does not exist as well. And that'd be a little bit incorrect. What I want to do is I want to go back to the graph here. So I want to sort of stop at this point right here, and I want to look at a graph of 1 over x minus 1 squared. And I've got that right over here on this slide. This is a graph of 1 over x minus 1 squared. And again, let's look at that left and right sided limits. Let me do this in red. So I got f of x equals 1 over x minus 1 squared. And we're going to look at the left and right sided limits as x approaches 1 from each side. And what you should see here is that both of these limits go to infinity, positive infinity. As my x approaches 1 from the left-hand side, my y just gets bigger and bigger and bigger and bigger until it just reaches infinity. So the limit as x approaches 1 from the right of 1 over x minus 1 squared is also positive infinity. And now we can do exactly what we've been doing with these left and right-sided limits. We can say, hey, the left and right-sided limits, they match. They're both positive infinity. So my limit here is going to just be positive infinity. And so that allows us to come back here and look at our work here, and we can sort of pick and choose here. This is our answer, this infinity. I don't have that does not exist or negative infinity. So the difference between these two examples is a great way of showing that while algebraically you could get 1 over 0 in two different cases, they can still lead to different answers. And so a graph is necessary in order to see, exactly where this limit is. Because really you're trying to look at left and right-sided limits and see if they match. And in that first example, they didn't match, so we got does not exist. In this example, they do match and they both go to positive infinity. So we're going to say that the limit here is equal to infinity. And yeah, so I could write that in here. I could add that in. I could say equals infinity, and then we're good. That'd be our answer. Awesome. So we've got two examples there. That's all good. Let's go ahead and look at another example here. But what I'm going to do here is I'm going to make it an example that's tough to graph. So presumably you could graph 1 over x minus 1 squared off the top of your head. You could graph it a lot easier than the next example I'll show. And this graph right here, this 1 over x minus 1, that should definitely be, you should definitely be able to graph that off the top of your head. So in these examples, they were fairly simple to graph. Let me go ahead and skip past this work that I've already done. Now let's go ahead and look at this example. Limit as x approaches 0 of 5 plus x over x times x minus 2. I would be at a loss on how to graph this by hand. This is not something that I would expect you to graph by hand. This is not something that I could even graph quickly by hand right now. So what we can do is we can start off with a direct substitution like we always do. No surprises there. And you can probably see that because of that x in the denominator, I'm going to end up with something over 0. Let's go ahead and write out that work and we'll see. So I'm going to direct sub, and so I'm not going to bother writing my limit anymore because I'm evaluating my limit. This is just 5 over 0. And again, we ask ourselves, all right, so is this going to be infinity? Is it going to be does not exist? Is it going to be negative infinity? And we're not sure about which that is. So it would be great if we could graph this, because then we could just look at the left and right-sided limits, and then we could see if they match. And if they match, then we've got our answer. If they don't match, we know that it's DNE. But like I've said, this is difficult to graph. So there's a way that we can do this algebraically, and the notation is a little bit new. It's a little bit different, but bear with me as I go through it. I'll explain it slowly. So if we do this algebraically, what I want to do is I want to look at the left and right-sided limits totally separately. So I'm going to do the limit as x approaches 0 from the right first. So I've got my 5 plus x over x times x minus 2. Tough to graph, so we're going to do this with just looking at this algebraically. So I'm going to do the right-sided limit first. And what I'm going to do is I'm actually going to do a direct substitution. And the thing that I want us to keep in mind is that this 0 plus right here that I'm plugging in, it's still 0. It's just that I'm approaching 0 from the right-hand side. You could say from the positive side. It'd be like me starting at 1 and counting down 0.9, 0.8, 0.7, 0.6, all the way down, 0.2, 0.1, and then 0. And so I'm approaching 0 from positive values. It's still 0, but it's just the way that I'm approaching it slightly changes. So let's go ahead and do this. Let's do this direct substitution. Let's plug in 0 from the right. And I'll go ahead and put that little plus superscript in a different color so we can highlight that. So we've got those 0 to the rights in there. And then let's just go through this part by part and be very careful with it. If I work this out, I'm just going to look at this top part. Let's just look at the numerator right now. If I take 5 and I add 0 to it, what am I going to get? Well, I'm going to get 5, right? That's fairly simple math right there. What you could say, though, if you wanted to, was because this 0 is being approached from the right, you could think about it in your head as that I'm taking 5 and I'm adding an extremely, extremely small positive number. Now, because it's so small and we're effectively treating it like a 0, I still get 5 when I add it to it. But I want to make sure to distinguish that it's 5 from the right. And that's helpful there, because that lets me know that my value here, it's 5, but from the right-hand side. And so we'll just move on from there. Let's go ahead and let's just copy down this guy here, 0 from the right, multiplied by, and now this one's a little bit tricky. So I've got 0 from the right, and then I'm subtracting 2. So if we were to draw a number line here, let's go ahead and do that. Here's 0. And if I'm looking at 0 from the right, I'm kind of looking at something like right there. It's still 0, but it's being approached from the right side. So if I subtract 2 off of this, I'm going to get to -2, right? I'm going to get to -2, but that -2 is going to be approached from the right-hand side, just like that 0 is being approached from the right-hand side. And so what I could say here is that this part in the parentheses on the denominator is -2, but from the right. And that's all good. Now, if I take 0, so let's go ahead and look at this denominator. If I take 0 and I multiply it by -2, I'm going to get 0. That doesn't change. Having these little, orange pluses anywhere, that doesn't change anything. If I do 0 times -2, I get a 0. That's good. But the question is that 0 being approached from the right or the left? And as we can see here, it's being approached from the right, so it's slightly positive. And what I'm doing is I'm taking this slightly positive 0 and I am multiplying it by a negative number. So what that actually does is, while I'm still getting 0 from the result of that multiplication, it ends up being a 0 from the left. And that's a key distinction here. So let me explain that again. Let me repeat that. I take 0 times -2. That's going to be 0. But because I'm multiplying this 0 by a negative number, it effectively, you can think about it as a negative number. And that's why I write 0 from the left, because it's just a very small negative number. What I could do here is I could just write out an example. Let's go ahead and say, let's say I did 0.1 and I multiplied that by -2. So in effect, I'm going to kind of treat this 0 plus, this 0 from the right, as a 0.1. Obviously, it's not the same thing as 0.1 because this is still 0 up here. But just for this purpose, let's pretend that it's a 0.1. If I do this multiplication, I get -0.2, which is a really small number. It's basically 0, but it's negative. And that's exactly why I write that negative superscript here. I say, hey, it's 0 from the left, because yes, it's still 0, but as you can very clearly see, it's negative, right? So that's why I get that 0 from the left. On the numerator here, 5 from the right, from the positive side, that's just 5. It wouldn't matter if it was 5 from the right or 5 from the left. It's still positive, right? So I can just sort of ignore that. I can just say, hey, it's 5, because whether this was a plus or a minus, the number is still 5, and 5 is still positive. I'm not on either side of the positive negative number line. So we're wrapping this up here. We're looking at our final part, which says that we've got 5 divided by 0 from the left. And remember, treat that 0 from the left still as a 0, but like a very small negative number. And if you want, you can think about it as that negative 0.2. So if I take 5 and I divide it by an extremely small negative number, I'm going to get negative infinity. And that right there, that actually tells us what our right-sided limit is. It's negative infinity. And that's part of our answer there. We obviously want the left and the right-sided limits in conjunction with each other, but let's go ahead and just take that there. So now I'm going to do the left-sided limit, and I'll do this a little bit more quickly since we just spent all that time on the right-sided limit. So let's go from 0 from the left, 5 plus x over x times x minus 2. And I'm going to do my direct substitution, and I'll get rid of that limit sign. I'm going to have 5 plus 0 from the left all over 0 from the left times 0 from the left minus 2. So when I work this out, my 5 plus 0 is still a 5. If I want, I could emphasize that it's from the left. And then I'm going to have 0 from the left multiplied by a negative 2, and I can emphasize that it's from the left. Now, when I do this multiplication on the denominator, I'm going to have 0 from the left, which is an ever so slightly negative number, and that's being multiplied by negative 2, right? And so if I take that very, very small negative number, very small, basically 0, but it's a very, very small negative number, and I multiply it by another negative number, that's going to give me something positive. So I could say that this is 5, and I could emphasize from the left if I want to, over 0. And remember I said it's a very slightly positive number, so it's 0 from the right. And in this case, I am taking 5, sure, 5 from the left, so maybe you think about it as 4.9, but it's still 5, it's a positive number, and I'm dividing that by 0, but you could think of it as ever so slightly positive. That's going to give me positive infinity here. And I just realized, oh no, that's good. And I had negative infinity here. I had positive infinity here. So because my left and right-sided limits are not equal, left not equal to right, that means that my limit as x approaches just 0 is not going to exist. And that's going to be our final answer right there that we can say. We can box that. We could say it does not exist. And with that, we were able to give ourselves an answer for this without actually graphing it. And that's going to kind of wrap up asymptote limits right there. You could do things graphically. You can do things algebraically. Algebraic is helpful in some cases like this if it's tough to graph, but a lot of times you'll just be able to graph that limit. So let's go ahead and go to sort of the bridge between these asymptote limits and infinite limits. I'm going to start off by filling in some of these asymptote limits. So let's take a look at this second limit here. I want to look at the limit as x approaches 1 from the left-hand side. And so if that's me looking here, my function goes down to negative infinity. So this limit is going to be negative infinity. As I approach 1 from the right-hand side, that's me looking here, my y values go up and up and up to positive infinity. So I'm going to say positive infinity there. That tells me that my limit as x approaches 1 does not exist because my left and right limits are not the same thing. So that's kind of just a little recap on the asymptote limits. Now on this same slide here, what I've got is I have, so those asymptote limits above this pink line, and I've got infinite limits below the pink line. And I haven't talked about infinite limits yet. This is the first introduction to it. So let's go through this slowly. Let's take a look at this notation first off. I have a limit as x approaches infinity right here. X isn't approaching a number anymore. So far, the only limits that we've seen is where x approaches, 1, or maybe 1 from the left or 1 from the right, or it approaches some number. But now I'm saying that it goes to infinity. And so what I'm doing there is I'm saying, all right, here's my x-axis. I've got that. I'm going to let my x get bigger and bigger and bigger and bigger. And I'm just going to keep on going until I get way out here, all the way out towards infinity. And the question that we want to ask ourselves is, what do my y values approach as my x gets really, really, really big? And you should be able to tell here that the function starts to approach 0. It starts to approach a y value of 0 as my x gets really, really big. So if I had x equals 1,000, this guy is going to keep coming down. I'm going to get way out here, and I'm going to look at x equals 1,000. I'm going to say it's basically 0. And so this limit as x gets larger and larger, as x approaches infinity, we can say that that is equal to 0, right? And this limit as x approaches negative infinity, it's basically the same thing. As x gets much more negative, so as it gets really, 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 really negative, and it keeps going sort of step by step, as I just get more and more negative, my y values on the function approach 0 again. And so we'd say this limit as x approaches negative infinity is going to be 0 as well. And those are infinite limits. So those are limits where the infinity is in your limit right here. And that's the key distinction between these infinite limits and the asymptote limits. The asymptote limits generally have an answer that involves infinity. The infinite limits have your infinity as your argument. It's where your x is approaching. And that's kind of just the difference in those names of those things. So let's move away from asymptote limits. Let's just talk about infinite limits now. And this is your end-all be-all fact. This slide is probably the most important slide of this lecture. This is something that you'll need to know. You'll need to understand this. And it's just that if basically what we're saying here is if I do 1 divided by infinity, that's 0. That's really what this is getting at. But it's saying if I take 1 divided cubed, it could be 1 over square root of x, because that's x to the 1/2. If I take a limit as x approaches either plus or minus infinity here, in all of these cases, it does not matter whether my limit is plus or minus infinity. Every single time, if my limit looks like this, which all of these in the red here do, then my answer is just going to be 0, right? And we saw that. We saw that on this graph here, right? I had a graph, this function here, f of x, I haven't explicitly written it out, but it looks like a 1 over x function. And so that actually tells me, hey, the limit is going to be 0. So basically what I'm getting at here is that if I have 1 over x raised to any power, I'm going to get 0 there. Some careful things that you want to note about this value of n. If n is equal to 0, that could trip us up, because if n is equal to 0, then x to the n would just be 1. So you want to be careful there. And then as well, you could have n be negative. You'd want to be careful on that. So if n is less than 0, you want to be careful. And yeah, and also, I won't go into much detail about this right now because we'll see examples of this. Sometimes things can be weird when x goes to negative infinity. We'll look at examples of that later. So just keep an eye out for that. Just sort of remember that can be weird. Yeah, let's go ahead and talk about how to actually do these infinite limits. So most of the time when I give you an infinite limit, when I have either a plus or a minus infinity in this argument as x approaches plus or minus infinity, generally I'm going to give you a rational function here. It's going to be one part divided by another part, and most of the time they're going to be polynomials. So we're keeping things pretty restricted. We're keeping things pretty simple here. But basically, you're going to have a polynomial divided by a polynomial every time. What you're going to do is you're going to take the entire polynomial here. So you're going to take this entire rational expression. You're going to divide every single term in it by the largest power that appears in the denominator. And I know what I just said, you're probably looking at that like, what is he talking about? Let me do an example, and then I'll come right back to this slide and I'll explain it again. So with this example here, like I said, when I give you this infinite limit, I'm going to give you a rational function, and it's going to be a polynomial on the top, in this case just a line, and it's also going to be a polynomial on the bottom, also just a line. And so what this slide is saying here, I'm going to find the largest power that appears in the denominator. And when I do that, when I find my largest power that appears in the denominator, I'm going to say, hey, this x here is the largest power. It's x to the 1, right? There's an x to the 0 here, but this is my largest power, right? If this was an x squared would be my largest power. But in this case, it's just x to the 1 is my largest power. So what I'm going to do is I'm going to take every single term in this limit, and I am going to divide it by that largest power, which, as I just said, was x. So I'm going to take that 5, I'm going to divide it by x. I'm going to take 6x, and I'm going to divide it by x. I'm going to take 2x, and I'm going to divide it by x. I'm going to take 3, and I'm going to divide it by x. Now, you might be looking at this and wondering, wait, how in the world is that even algebraically allowed? How are these the same thing at all? And basically what I'm doing here is by dividing everything by an x, everything sort of negates itself. You could think about this as though I'm taking this limit here. Let me go ahead and copy this. I'll actually just write this out and show you. So how you could think about this is that I take this limit here, and I'm going to multiply everything by 1, actually. So again, just to be clear, I'm just showing how I go from here to here. That's all I'm doing right now. So if I take this and I multiply by 1 over x divided by 1 over x, that's a legal operation because what's in the orange is just equal to 1. And then I can just sort of distribute that 1 over x in, and I get exactly what I had on that last slide. And right here, I'm just distributing. And right there, we're at the exact same part that we're at right here. So that's good. So we can do this, and let me now go back to that slide with the definition again and those steps, just to highlight what I've done here. I have found the largest power in the denominator, which in this case was x, and I took that x and I divided every single term in the function. I divided every term by that x right there. And that is going to be our steps for how we go through and solve these infinite limits. So at this point here, I'm actually going to use a limit property, right? And let's go ahead and do that. So if we use our limit property, we can remember that we had that sum and difference property, and we also had the quotient property. And I'm going to go ahead and do that here just because I got a little bit more space. So let's take that limit property here, and let's do this. Limit as x approaches infinity of 5 over x. I'll go ahead and write that like that. Minus limit as x approaches infinity of 6x over x. Obviously, I can simplify that in a second, and that's what I'll do next. Limit as x approaches infinity of 2x over x plus the limit as x approaches infinity of 3 over x. And so I'm using limit properties here, and I'm mixing the sum and difference properties with the quotient properties. And that's going to take me to this stage right here. And at this point, well, let me actually, before I say that, let me do the simplification. You can see here that my x's are going to cancel. And you can see here that my x's are going to cancel. That's good. Let's go ahead and do that. I'll copy this guy over onto a new page. And what do we have? We had limit as x approaches infinity of 5 minus 6x over 2x plus 3. That's good. We've got that. We've done some algebra. It's simplified here. Let's go ahead and actually simplify. I know this is kind of annoying writing limit over and over, but it's very important because if you don't write limit, it's just not a limit anymore, and that's bad. Great. So right now, we've got 4 limits. We've got one here. We've got one here. We've got one here. And we've got one here. And I can do each of these 4 limits just independently, and that's fine. That works out. This is just me going on and doing my algebra. I can do each of these limits independently. And let's look at this red limit first. That's a limit as x approaches infinity of 5 over x. And remember, I talked about this in this slide back here that was very important. This right here looks an awful lot like that red limit we were just trying to do. There's an x going to either a plus or minus infinity, and it's like a 1 over an x, right? I have that x on that denominator. And so we see that here. It doesn't matter that there's a 5 there. That's just a constant. If you wanted to, you could pull the 5 out here using your limit properties. The point being, this limit is going to be 0. And that's exactly what we're going to have there. Then in the orange, that's a straightforward limit. There is no x in the limit here, so it's just 6. It doesn't matter what x approaches. It's just the function 6. So the answer for the limit is always 6. Very similarly, in the green, we're just going to have 2. And then in the pink, it's going to be basically the same thing as what we just did in the red. It's going to just be 0. We're going to use that sort of definition, if you will, or that fact right here, that the limit of 1 over an x is just 0. And so we've got that right there. I can do my last bit of simplification. I get -6/2, which is -3. Awesome. We got an answer. I love it. Now, hopefully some of you have recognized a mistake that I've made here. Not a mistake, but I've done things out of order. I started off on this limit here, and I forgot to do something right in the beginning. And that thing that I forgot to do was a direct substitution. Like I've said, we always got to start with a direct substitution. So shame on me for forgetting that, but that's okay. We'll do it now just to make sure we'll do it now just for good measure. So obviously we already have our answer, but let's say we went back and we started off and we did a direct substitution. I want to see what we get. So if I do my direct substitution, I'm going to have 5 minus 6 times infinity, I guess, and 2 times infinity plus 3. This is not something you'd see many mathematicians write. Infinity isn't actually a number, so you can't really use it as a number. Basically, this ends up as infinity over infinity. And so we're looking at that, and we're wondering what that is, right? What is that? Is that even an answer? Is that a viable answer? And it's not. This right here is an indeterminate form. Just like 0 over 0 was, infinity over infinity is an indeterminate form. And so if we had done things in the correct order here, we would have done this direct substitution first. We would have gotten this indeterminate form, infinity over infinity. Then we would have done this work right here. And again, look, this is just me doing some algebraic tricks to manipulate this so that it ends up in a form that I can work out. This is exactly what we did last lecture. We worked on those sort of magic tricks. We looked at, you know, hey, how can I algebraically manipulate a function and a limit so that it works out so that I don't get that indeterminate form anymore? And we did that, and we got -3 as our answer here. We didn't get infinity over infinity, and that's good. That's exactly what we're hoping for. So let's go ahead and do 2 more examples here, and we'll see this sort of same pattern in all of these. So again, it looks very similar, this problem. The only thing I've changed here is I've added a x squared instead of an x here. So let's go ahead and just work through this. So we're going to start off with limit as x approaches infinity of 5 minus 6x all over 2x squared plus 3. And remember, the step here, when we see that x approaching infinity, we go, this is an infinite limit. So the first thing that I need to do is I need to identify the largest power in the denominator. And that's going to be that x squared. And what we're going to do is we're going to divide every term by a 1 over an x squared. So I've identified that x squared is that largest power. So I'm going to divide every term by it. That division by dividing every term by x squared, that's the same thing as multiplying everything by a 1 over x squared. So just showing that intermediary step right above there. I'll have 5 over x squared minus 6x over x squared all over 2x squared over x squared plus 3 over x squared. And we can do some simplification here. Still just a 5 over x squared. Here an x will cancel. That's good. That's helpful. Here we just get a 2. And here we have 3 over x squared. Now, I can write out my limit properties. I can split this up into those 4 limits that we saw before. Just for the sake of time, I'm not going to bother writing out each of those 4 limits. You can see, hopefully clearly, that I'm just going to sort of do this limit on each of these 4 parts, right? And so if I do that, for the first part, I have a limit of 5 over x squared as x approaches infinity. And again, that's that fact, that's that useful fact that we saw before. It's 5 over x squared. And so when I take a limit as x approaches infinity, that goes to 0. So I can go ahead and just write 0 there. And then I'm going to subtract off this limit here, limit as x approaches infinity of 6 over x, and that's the same deal. That's the same concept. We're doing 6 over x as x goes to infinity. That's going to go to 0. That's fine. That's all good. I can do this limit here, and like we saw before, that's just 2. It doesn't matter that x is going to infinity. The function is just 2 always. There's no x in it. So I just get 2 for that limit, and that's all good. And then I can subtract off this limit here. So limit as x approaches infinity of 3 over x squared. We've already done 2 of these on this problem. That's just going to be 0 again. And so I do some simplification. I get 0 over 2. And don't get tripped up and think that that's an indeterminate form. 0 divided by a number, it's just 0. This is just asking, hey, how many times does 2 go into 0? Well, none. And there's our answer right there. We get 0. Great. There we go. We've got another example in the books. Let's do one last example here. And I'll skip through this work because I just worked on all of it. So again, very similar, but what I've done here is I've let this be a 2x and I've added a squared up here. So let's go ahead. I'll add a new page and we can just work this out. 5 minus 6x squared over 2x plus 3. Infinite limit, I see that infinity right here. So I'm going to start off by identifying the largest degree in the denominator, the largest power, and I see that that's just x. So now I'm going to divide every single term by x because that's the largest power in the denominator. Get my 5 over x, my 6x squared over x, I get a 2x over x, and I get a 3 over x. I can then simplify. Some x's cancel nicely. That's good. We get 6x. I get a 2. And I get my 3 over x. Now, I didn't do this last time. I didn't write out that limit property work, but I actually want to do that here. So I'm just using that quotient rule, and then I'm using that sum and difference rule, or property, I should say. And I'm going to highlight 3 of these limits here, because 3 of these limits we've actually done already. We've seen them. I'm going to highlight this guy. I'm going to highlight this guy. And I'm going to highlight this guy right here. Let's actually just evaluate those. I'm going to get 0 for this orange limit. That's good. I'm going to get 2 for the green limit. And for the pink limit, I'm going to get 0. Now I've left off this limit here that I'll box in red. And if I look at that limit, that's a limit as x approaches infinity of 6x. Let's go ahead and graph 6x really quickly. Just a real quick sketch. Looks something like that. And there we go. As x approaches infinity here, my y values also approach infinity. You could also just do a direct sub, plug the infinity in for x here, and you'll see that you get infinity. So this red limit here is infinity. And now I have 0 minus infinity on the numerator. That's just going to be minus infinity. And then I have 2 on the denominator. Well, minus infinity divided by 2 is just minus infinity. That infinity is sort of dominating over things in this case. And so my answer here is minus infinity. That is a viable answer. We are okay with that. And we've seen that by splitting these limits, splitting this one limit into 4 different limits using limit properties, and identifying that this red limit, this limit of 6x, if I look on a graph, that limit is infinity. And so I get that infinity here. Don't forget that little negative sign that sort of keeps carrying down over and over. And so we get negative infinity for our answer. What you should have, well, maybe not should have noticed, but you might have noticed these 3 limits that I just gave us for these examples. They were 5 minus 6x over 2x plus 3. There was a limit as x approaches infinity of 5 minus 6x over 2x squared plus 3. And there was a limit of 5 minus 6x squared over 2x plus 3. And what I've done here with these examples is I've actually just changed the degree of the function. You'll notice here that I have, this is like an x over an x, which is kind of like a 1. This right here is an x over an x squared, which is kind of like a 1 over x. This right here is an x squared over an x, which is kind of like x. Really, the point that I'm making here is in this first example, my degree was the same on the top and the bottom. In this second example, my degree was larger on the bottom. And in this third example, my degree was larger on the top. I encourage you guys to look at the answers that I had for these. I'll go ahead and write them down right here. We had -3 here. We had 0. And we had negative infinity. I encourage you to look at those answers and see if you can sort of find a pattern with what I've just described. And I'll go ahead and leave you guys to do that and end our big 4-part lecture on limits, and that'll be it.